Section: Introduction. In this section, we explore the vulnerabilities of large language models, LLMs, and categorize them into three main types: model-based vulnerabilities, training time vulnerabilities, and inference time vulnerabilities. We also examine various strategies to mitigate each type of attack. Model-based vulnerabilities stem from the fundamental design and structure of LLMs. Notable examples include model extraction, model leaching, and model imitation attacks. We will provide a brief overview of these attacks and discuss potential strategies to counter them. Model extraction attacks occur when an attacker tries to uncover specific details about a deployed LLM-based service. Essentially, adversaries aim to steal the model by querying the service. It's important to recognize that training an LLM with over 1 billion parameters, like GPT-4 or Mistral, is both expensive and complex, making it difficult for many to replicate. As a result, attackers look to reveal the characteristics of the model, which can lead to significant losses for the owners. One common approach in model extraction involves offering a cheaper service by leveraging an existing LLM through an API. For instance, an attacker might use an LLM that costs a certain amount while creating a similar service that costs less. In this scenario, the attacker modifies the prompts to reduce the number of tokens used, allowing them to generate similar outputs while profiting from the difference in cost. By understanding these vulnerabilities and their implications, we can better develop strategies to protect LLMs from adversarial attacks and enhance their overall security. Section Summary. In this section, we explore the vulnerabilities of large language models, LLMs, categorizing them into model-based, training time, and inference time vulnerabilities, while also examining various mitigation strategies for each type of attack. We highlight the risks of adversarial attacks, such as model extraction, which can lead to significant losses for LLM owners, and emphasize the importance of understanding these vulnerabilities to enhance the security and resilience of LLMs in real-world applications. Section: Mitigation Strategies. In this section, we discuss various strategies to mitigate issues related to model imitation. To tackle these problems, Goody-Banday et al. Suggest that we should gather a highly diverse imitation dataset. We need to be careful when transferring knowledge from proprietary models, avoiding the temptation to simply copy their outputs. Instead, we should selectively fine-tune our models on relevant tasks while ensuring that we maintain transparency and interpretability. Additionally, we can apply regularization methods during training to avoid overfitting to the outputs of proprietary models. Introducing adversarial examples during training can also help us build robustness and address any biases that may exist in proprietary models. Furthermore, we are encouraged to explore and develop open-source alternatives that do not depend on proprietary models. It is crucial to consider ethical guidelines to ensure that our model behaviors align with societal and ethical standards, rather than just imitating existing models. Next, we examine model leaching attacks. This type of attack involves extracting specific knowledge from a target large language model, LLM, to create a smaller model with fewer parameters. Typically, this process includes crafting prompts that elicit specific responses from the target LLM, analyzing the characteristics of the model being extracted, and then building a new model by copying these task-specific characteristics. The goal of model leaching is to design clever prompts that generate responses we can use to train a new language model, all while working within a limited number of queries. By using this newly trained model on the generated responses, a malicious user can evaluate the limitations and vulnerabilities of the original LLM, which can help identify effective strategies for further attacks. We also note that as new LLMs and their APIs become available, the practice of model imitation has become more significant. This involves gathering insights from an existing model, often through API calls, and then fine-tuning our own model with this information. This is particularly relevant for open-source language models or those aiming to compete with proprietary models by leveraging their outputs. Research papers like Alpaca, Vicuña, and Koala have documented successful attempts to imitate proprietary LLMs in terms of performance. However, We must recognize that while open-source models can gain from insights provided by proprietary models, they still face limitations, especially in areas like factual accuracy, coding, and problem-solving. The work by Goody-Banday et al. Highlights that open-source models can improve by utilizing proprietary LLMs, but they still struggle in certain aspects. We then turn to training time vulnerabilities, which include attacks that occur during the model's training phase. Key issues in this area involve data poisoning, where harmful data is inserted into the training set, and backdoor attacks, which embed hidden triggers within the model. We will explore these issues in more detail. Data poisoning refers to a type of attack where malicious data is subtly added to an AI model's training set. This covert approach creates hidden vulnerabilities that can compromise the model's integrity and functionality. Wan et al. Demonstrate how data poisoning can affect LLMs like ChatGPT, showing that even a small number of poisoned samples can lead to problematic outputs. Their experiments indicate that as few as around 100 poisoned examples can cause unintended results across various tasks. This serves as a warning for us to remain vigilant about this threat and to consider strategies for mitigation. For backdoor attacks that manipulate the input space, a common strategy is to identify the underlying trigger. One technique, known as bad prompt, automatically generates effective triggers for individual samples. Other strategies include filtering out inappropriate prompts to minimize the risk of injecting harmful instructions into the model, using publicly available datasets instead of relying solely on self-collected data to reduce exposure to potentially manipulated data during training, and utilizing third-party platforms to lessen the computational load during LLM training. We can also start with pre-trained models and fine-tune them using specific prompts and instructions tailored to our desired tasks, which helps maintain security while allowing for customization. Finally, we discuss backdoor attacks, which involve embedding a hidden trigger within the LLM using a malicious agent during training. The triggering effect is activated only during the inference phase, causing the model to produce unintended outputs. Compared to data poisoning, backdoor attacks can be more subtle and often go unnoticed until the trigger is activated, at which point it may be too late to address the issue. One method of executing a backdoor attack involves exploiting the input space by using specific mechanisms within the prompt, such as uncommon words or short phrases. Another approach uses the embedding space, where backdoors can be injected through word embedding vectors. A more impactful method is to embed the backdoor within the encoder module of pre-trained LLMs, as seen in the notable example, which uses an adaptive verbalizer to connect triggers to specific words. Section Summary. In this section, we outline various mitigation strategies to combat model imitation and extraction issues, emphasizing the importance of creating diverse datasets, cautious knowledge transfer, and maintaining ethical guidelines. We also discuss vulnerabilities during training, such as data poisoning and backdoor attacks, and suggest methods like identifying triggers and using pre-trained models to enhance security while customizing LLMs. Section: Inference Time Vulnerabilities. In this section, we focus on vulnerabilities that arise during the interaction between models and end users or systems. This includes various types of attacks such as jailbreaking, paraphrasing, spoofing, and prompt injection, each taking advantage of how the model responds in different ways. When we talk about a paraphrasing attack, we refer to a method where an adversary alters the input text sent to a large language model, LLM, using another model designed for paraphrasing. The goal here is to change the text while keeping its original meaning intact. By doing this, these attacks can avoid detection or safeguards that depend on specific patterns in the text generated by the LLM. This technique can also be misused for harmful purposes like plagiarism or creating misleading content. Next, we consider spoofing attacks, which involve an adversary mimicking an LLM by using a modified version of it to produce similar outputs. This manipulation can lead to harmful, misleading, or inconsistent results. For example, a spoofed LLM chatbot might make offensive remarks, spread false information, or unintentionally disclose sensitive information. The consequences of spoofing attacks can jeopardize the security and privacy of systems that rely on LLMs. It's important to note that while model imitation focuses on adapting existing models, spoofing is about creating a deceptive imitation with the intent to mislead. Therefore, we should not confuse these two types of attacks, as their purposes and effects are quite different. To combat these vulnerabilities, we can employ various mitigation strategies. One common approach is to analyze each token in a prompt to see how it affects subsequent tasks. Another effective strategy is to filter out unusual tokens that might degrade performance. Suo and colleagues have introduced a method called signed prompt, which helps prevent prompt injection attacks in applications using LLMs. This method uses digitally signed instructions from a trusted source to verify that the instructions given to the LLM are legitimate. Other strategies include validating and sanitizing user inputs to block harmful instructions, considering the context of the instructions, and dynamically adjusting defenses based on how the system behaves. We also address jailbreaking privacy attacks, which involve manipulating input prompts to bypass built-in safety features. This raises significant concerns about security, privacy, and ethical use. Researchers, including Lee and others, have shown that while ChatGPT can withstand direct prompt attacks, it is still vulnerable to more complex jailbreaking attempts that could lead to unauthorized access to sensitive information. The evolving nature of these tactics is highlighted by Shen and colleagues, who analyzed numerous real-world prompts and found a concerning trend toward more subtle and sophisticated methods, with attackers moving from public to private platforms. This shift complicates proactive detection efforts and demonstrates how adaptable attackers can be. Their study also revealed that some jailbreak prompts can be highly effective, achieving success rates as high as 99% on platforms like ChatGPT and GPT-4. Additionally, Rao and others have proposed a structured classification of jailbreak prompts based on language changes, the attacker's intent, and the method of attack. This organized approach emphasizes the need for ongoing research and the development of flexible defensive strategies, as well as the importance of understanding various attack intents, such as goal hijacking and prompt leaking. Finally, we explore direct and indirect prompt injection attacks. These attacks allow adversaries to take control of a model's output or even reveal its training data. In direct prompt injection, an adversary carefully crafts inputs to exploit the model's biases or knowledge, prompting it to produce specific or misleading outputs. Prompt leaking, a more focused form of this attack, occurs when the model repeats its own prompt in its response. A common strategy for prompt injection is to trick LLMs by inserting triggers, like common or unusual words, symbols, or sentences, into the prompt. For example, the advocal method uses word-level changes, such as adding, removing, swapping, or substituting characters, to attack few-shot examples. Kong and colleagues delve deeper into LLMs, particularly those skilled at following instructions, like ChatGPT. They point out an ironic situation. The better these models are at following instructions, the more vulnerable they become. When presented with carefully crafted prompts, they can generate harmful outputs, including hate speech or conspiracy theories. This adds a new layer of complexity to the security challenges surrounding LLMs, suggesting that their advanced capabilities might also be their greatest weakness. Greshake and others have identified a new threat called indirect prompt injection. In this scenario, adversaries cleverly embed prompts within external resources that LLMs access, such as websites. This approach differs from traditional direct interactions with LLMs, allowing attackers to exploit them from a distance. Such attacks can lead to serious risks, including data theft, spreading malware, and manipulating content. This finding highlights a significant shift in how LLMs can be exploited, broadening the range of potential vulnerabilities we need to consider. Section Summary. In this section, we explore various inference time vulnerabilities in language models, including paraphrasing, spoofing, and jailbreaking attacks, which exploit the model's response mechanisms to achieve malicious outcomes. We also discuss mitigation strategies, such as validating user input and employing techniques like signed prompt to enhance security against these evolving threats. Section: Prompt Leaking. In this section, we explore the concept of prompt leaking, as discussed by Perez et al. They focus on how prompt manipulation can lead to issues with large language models, LLMs, such as GPT-3. They show that these models can be misled from their intended purposes through techniques like goal hijacking or by exposing sensitive training prompts. Their work introduces the PROMPTINJECT framework, which successfully circumvents the content filtering measures of OpenAI, demonstrating how effective their method is in altering LLM behavior. Collectively, these studies highlight the significant challenges and risks tied to prompt manipulation in LLMs. They stress the importance of understanding both the technical strengths and potential weaknesses of these advanced AI systems, underlining the necessity for strong security and privacy measures. Next, we address the issue of altering LLM behavior through model editing. LLMs have gained immense popularity across various domains, but a major challenge arises due to the vast number of parameters they contain, often in the billions. This leads us to ask, how can we reduce unwanted behaviors, like generating inappropriate content or giving incorrect answers, without needing to retrain the entire model? The solution lies in model editing, which involves changing aspects like architecture, parameters, or weights of LLMs to enhance their performance. Common practices in model editing include gradient editing, weight editing, memory-based editing, and ensemble editing. It's important to note that this approach requires access to the model's parameters, meaning that black box models may not be editable in this way. In this section, we will delve deeper into these editing methods. We begin with gradient editing, a technique that allows us to make adjustments to pre-trained LLMs after their initial training. As models increase in size, even initially accurate predictions can become erroneous over time, making it impossible to catch all mistakes during training. Therefore, it is beneficial to enable developers and users to correct these inaccuracies while maintaining the overall integrity of the model. An example of gradient editing is the model editor networks with gradient decomposition, or MEND. This method involves training a set of multi-layer perceptrons, MLPs, that adjust gradients to ensure that local changes do not adversely affect the model's performance on unrelated tasks. The MEND process consists of two phases, training and editing. Researchers have applied this method to various models, including T5, GPT, BERT, and BART, and have tested its effectiveness on datasets like ZSRE question answering, Fever fact-checking, and Wikitext generation. MEND has proven to be effective in modifying even the largest transformers, outperforming other methods in terms of the extent of changes made. Next, we discuss weight editing, which involves changing the weights or parameters of a pre-trained LLM. An example of this is Rank 1 model editing, or ROME, proposed by Meng et al. This method modifies the feed-forward weights within a neural network to assess how well the model recalls factual information. It examines neuron activations and adjusts weights to identify changes related to factual accuracy. In their work, they created a dataset of counterfactual assertions, known as COUNTERFACT, to evaluate these edits in LLMs. By using causal tracing, they identify the most important MLP modules for retaining factual information. This research emphasizes the significance of the middle layers in MLPs for recalling factual details. Effective weight editing requires a deep understanding of where the model stores specific information, which greatly influences the editing decisions we make. Evidence suggests that factual information is often found in the middle layers, while common sense knowledge is typically located in the earlier layers. Another example comes from Ilharco et al., who practice weight editing by creating task vectors. These vectors are formed by subtracting the weights of a pre-trained model from those of the same model after it has been fine-tuned for a specific task. These task vectors represent directions within the model's weight space. By combining and adjusting these vectors through operations like negation and addition, we can influence the model's behavior and improve its performance on particular tasks. We also examine memory-based model editing, a technique that enhances LLMs by making localized updates to their behavior. In this context, model editors modify pre-trained base models to inject new knowledge or correct undesirable behaviors. The goal is to improve the model's performance by fine-tuning specific aspects of its behavior, such as its predictions or responses. One notable method is Sirac, which uses external memory to enhance model behavior. This approach includes an external edit memory, a classifier, and a counterfactual model. Edits are stored in the memory and then classified and evaluated using the counterfactual model. If the edits are deemed relevant, they are incorporated into the model for updates. This method has been tested on models like T5 Large, BERT, and BB90M across various datasets, including question answering and fact-checking, showing impressive results. Another significant method is mass editing memory in a transformer, or MEMIT, which aims to improve LLMs by adding additional memories that can scale to a large size. The main goal of MEMIT is to modify the factual associations stored within the weights of LLMs. While ROME focuses on single edits, MEMIT can handle thousands of associations for models like GPT-J and GPT-Neox. Additionally, MEMIT allows for updates across parameters in multiple layers. Gupta et al. Extend this framework with MEMIT for Common Sense Knowledge, or MEMIT_CSK, to specifically address common sense knowledge, which differs from encyclopedic knowledge. While encyclopedic knowledge relates to subject-object relationships, common sense knowledge involves concepts and subject-verb pairs. MEMIT_CSK effectively corrects common sense errors and can be applied to editing subjects, objects, and verbs. Experiments show that common sense knowledge is more prevalent in the early layers of the model, while encyclopedic knowledge is typically found in the middle layers. Section Summary. In this section, we explore various methods for editing large language models, LLMs, to improve their behavior without complete retraining, including gradient editing, weight editing, and memory-based editing. We highlight techniques like MEND, ROME, and MEMIT, which allow for targeted modifications to model parameters and memory associations, ultimately enhancing performance and addressing undesirable outputs. Section: Ensemble Editing and Beyond. In this section, we discuss ensemble editing and its advancements. Ensemble editing involves combining various model editing techniques to create a stronger and more effective method. For example, Wang and colleagues introduce Easy Edit, a user-friendly framework for model editing that works across different large language models, LLMs. Easy Edit evaluates specific hyperparameters, such as certain layers or neurons, and uses customizable metrics to measure how effective the model editing is. The success of this framework is shown across several LLMs, including T5, GPT-J, GPT-Neo, GPT-2, Llama, and Llama 2, utilizing methods like ROME, MEMIT, and MEND, among others. Despite the progress in model editing, Yao and their team analyze how well these methods perform. They create a new dataset specifically for this analysis, focusing on two approaches to editing LLMs, one that preserves the model's parameters using an auxiliary model and another that directly alters the model's parameters. Their results emphasize the need for ongoing improvements in LLMs, especially regarding portability, locality, and efficiency. As the field evolves, enhancing model editing techniques becomes crucial for improving LLM performance. Additionally, recent studies look into how model editing affects language modeling. Hazra and colleagues find that ensuring factual accuracy during model editing can lead to unsafe behaviors in the model. On the other hand, Wang and their team propose a method called DINM, which detoxifies language models to ensure they generate safe content. Since model editing is still a relatively new area, more research is necessary to evaluate its effectiveness in addressing the vulnerabilities mentioned. Next, we introduce the concept of chroma teaming, which represents the collaboration among red, blue, green, and purple teams in LLM security. These teams work together towards a common goal: strengthening LLMs against adversarial attacks. Red and blue teaming are well-known terms in testing security vulnerabilities. Red teams simulate cyber attacks to find weaknesses, while blue teams focus on defense and prevention. With the rise of LLMs, a new research area has emerged that applies red teaming techniques from cybersecurity to evaluate adversarial threats to LLMs. It's important to clarify that while some researchers equate jailbreaking with red teaming, we see them as distinct. Jailbreaking often relates to privacy issues, while red teaming aims to highlight potential harms. The goal of red teaming is to uncover the negative outputs that LLMs can produce, which can include hate speech, violent statements, and inappropriate content. For example, a red teaming exercise might involve crafting a prompt designed to provoke the LLM into generating violent content. If the prompt successfully bypasses the model's defenses, the red teaming objective is met. Essentially, red teaming seeks to identify which prompts or strategies can evade an LLM's safeguards and result in undesirable outputs. Numerous studies have examined red teaming in the context of LLMs, revealing their strengths and weaknesses. Given its effectiveness, red teaming is crucial for understanding the potential negative impacts of LLMs. For instance, Joe and their team have investigated whether ChatGPT produces harmful outputs using prompt injection techniques, while other studies focus on specific aspects of red teaming, such as developing toxicity classifiers or using red teaming LLMs to spot risky outputs that might otherwise go unnoticed. A study by Ganguly and colleagues shows how different sampling techniques can influence red teaming efforts. For example, reinforcement learning with human feedback, RLHF, has demonstrated greater resilience compared to rejection sampling, although these methods often require significant human input. To reduce this manual effort, some researchers are looking for ways to automate red teaming. For instance, Lee and their team use Bayesian optimization to conduct red teaming with fewer queries and less reliance on human assistance. We also note the emergence of green teaming. Unlike red teaming, which focuses on identifying vulnerabilities, green teaming explores situations where seemingly unsafe content might still have beneficial uses. It recognizes that there are nuanced cases where language models generate content that could be seen as unsafe but serves a specific purpose. For example, using language models to create intentionally flawed code for educational reasons fits into this category. As green teaming gains traction, new variations of color teaming have developed alongside red teaming. One such variation is purple teaming, as discussed by Bott and colleagues, who focus on detecting insecure code generated by LLMs. They provide a benchmark to evaluate the cybersecurity safety of LLMs, drawing from both red and blue teaming concepts. Section Summary. In this section, we explore Ensemble Editing, which combines various model editing techniques to enhance the robustness of language models, LLMs, exemplified by Wang et al.'s Easy Edit framework that evaluates hyperparameters across multiple LLMs. We also discuss the collaborative efforts of red, blue, green, and purple teams in LLM security, highlighting the importance of red teaming in identifying vulnerabilities and the emerging concepts of green and purple teaming that focus on beneficial uses of potentially unsafe content and detecting insecure code, respectively. Section: Rainbow Teaming and Beyond. In this section, we discuss the concept of rainbow teaming, which goes beyond traditional red teaming. Rainbow teaming builds on red teaming by focusing on creating a wide variety of adversarial prompts. While red teaming mainly looks at how often we succeed, rainbow teaming emphasizes both success and the diversity of the prompts we generate. We achieve this by using feature descriptors and a mutation operator to develop new adversarial prompts. As we move forward, we anticipate that advancements in color teaming will lead to better strategies for countering adversarial attacks. We also expect new ideas and influences to arise, as seen with rainbow teaming. It is important for us to observe these trends, especially when working with different types or multiple modalities for large language models, LLMs. In summary, we believe it is essential to leverage the unique strengths of various teaming strategies through what we call chroma teaming. In this approach, red teaming helps us find vulnerabilities, Blue teaming protects against threats, green teaming fosters innovative solutions, and purple teaming merges insights from both red and blue teams to strengthen our overall resilience. Looking ahead, our research paper provides a thorough examination of LLM vulnerabilities and effective strategies, including chroma teaming and model editing, to address these issues. However, as we have noted throughout the paper, there are limitations and challenges with the current strategies, which open up opportunities for further progress in LLM security, vulnerability, and risk mitigation. These opportunities include, but are not limited to, 1. Analyzing LLM vulnerabilities at both the model architecture and model size levels. 2. Exploring how transfer learning and fine-tuning contribute to model vulnerabilities. 3. Identifying and addressing new types of attacks. 4. Assessing the effects of attacks on specific models. 5. Creating automated systems to lessen human reliance in color teaming. 6. Further investigating model editing across various datasets and model characteristics, such as 7. Layers and parameters, and 8. Developing a unified platform to test multiple model editing techniques.